Hello and thank you for coming to my talk. My name is Matthew Whittall and I'm here representing Embry-Riddle Aeronautical University, presenting work titled Spacecraft, Navigation and Control in Lie Group SE3 around small irregular bodies. This work has been performed with Gennaro Mangiaro-Capra and Elisa Capello of Torino Polytechnic University and Dr. Murad Nazari and Aku Apakanam at Embry-Riddle Aeronautical University. This work presents a novel rigid body spacecraft navigation and control architecture within the special Euclidean group SE3 and its tangent model TSE3 while considering stochastic processes in the system. This formulation effectively combines the translational and rotational motion of a rigid body spacecraft into a single compact set and presents the integration of a stochastic estimator-based controller for spacecraft motion in a highly nonlinear irregular-shaped small body environment using a novel TSE3 framework. After talking about the formulation, I will be talking about two cases in which we've applied this method. The first is around the small Saturnian moon Pan, where we were trying to maximize coverage of the surface, and a hovering problem around the small asteroid Bennu. The augmentation of the stochastic estimator in the almost globally asymptotically stable controller is thus proved to be a reliable, functional approach for spacecraft navigation control in a highly perturbed environment, such as around small bodies with irregular shapes. A spacecraft configuration is defined by 6 degrees of freedom, 3 of which are related to the position in space, and 3 are related to the position around its axis, its attitude. Conventional methods of attitude determination usually have minimal 3-parameter sets. However, these parameterizations have disadvantages, such as singularities and non-uniqueness. Other methods, such as quaternions, remove the disadvantage of singularities, but gain the disadvantage of being non-unique and redundant. Rotation matrices, such as what's used in the SE3 formulation, likewise are redundant, but do not have the disadvantage of being non-unique, nor do they experience singularities. Due to its compact form and associated Lie algebra, it has the potential to reduce computation time significantly and maintain and even improve accuracy as well. When position and attitude are considered together, such as they are in SE3, it may be referred to as a spacecraft's pose. SE3 is a smooth manifold which obeys group properties, but has the additional condition that group operators are differentiable. SE3 is defined as follows, where little r is the position and a member of R3, and capital R is the rotation matrix and a member of R3 by 3. Since this matrix is smooth, there exists a single tangent space at each point, which may be represented as the Lie algebra, where v and omega are the velocity and attitude rate vectors, and cross and v are the skew and wedge operators respectively. For more details on the SE3 formulation, you can look at the paper or references 22 or 23 in the paper. But for the purposes of this presentation, the most important part is the system formulation on SE3. The rigid body kinematics and kinematic equations of motion are given here, where g dot is the differential of g presented earlier, and the differential velocity and attitude rate are controlled by the coadjoint operator defined here, the inertia tensor in SE3 defined here, and the rigid body augmented velocity vector with inputs u sub g and u sub c, which are the control inputs from the external gravitational perturbations and the control input respectively. Intuitively, this operator allows for the transformation of a tangent vector from one tangent space around one element to the tangent space around another. Now let's take a moment to talk about the dynamics of the system. Dynamics were based on a 2015 paper by Misra, Izzati, Sanyal, and Shears, which displayed the efficacy of navigation in SE3 around small bodies with unknown harmonics. The potential term given here, where rho is the position vector, mu is the gravitational parameter, and C22 and C20 are the second degree and order coefficients and may be defined by these two equations, where alpha, beta, and gamma terms are normalized parameterizations of any given triaxial ellipsoid. By taking the partial derivative of u with respect to rho and integrating over the body of the spacecraft, keeping only terms on the order of 1 over rho to the 4th, we are left with these terms, where J is the inertia matrix, R is the center of mass of the spacecraft with respect to the center of mass of the central body in the body-centered inertial frame, and the non-spherical parameters of the body here in the body-centered body-fixed frame. Additionally, the gravity gradient torque on the rigid body spacecraft due to the central body can be expressed by this equation, which of course is expressed in the spacecraft body fixed frame. In terms of stochasticity, noise can take two forms, either process noise or measurement noise, represented here as eta and zeta respectively. That noise may be present about the attitude, the position, attitude rate, velocity, or any combination thereof. but can adequately be shown in compact form as the noise about G or about V. Again, these are assumed to be Gaussian white noises with zero mean and to be uncorrelated. In Euclidean space, the noise is treated with an additive approach. But since SE3 is a nonlinear manifold, a novel formulation for stochastic systems on TSE3 is introduced. This method accommodates stochastic processes in vectorial space by implementing the exponential map to SE3, where chi is the noise in SE3 around this Gaussian distribution in Euclidean space. These errors are then treated with a Kalman filter, which is a common solution to the problem of spacecraft navigation. The Unscented Kalman filter specifically is advantageous because it avoids the linearization of errors because it doesn't require the use of a Jacobian, as is the case with an extended Kalman filter. The UKF does not, however, ensure global convergence, so the estimated state should be selected initially close to the true states to ensure at least local convergence. The design of a UKF requires system knowledge and is defined by nonlinear state transition and measurement functions defined here for SE3 and a retraction function, which is defined here, which take the formulation from R12 to TSC3 and back again through the use of its inverse. The UKF is characterized by two main phases, prediction and correction. To perform the prediction, a set of points, known as sigma points, shown here, are propagated through the nonlinearities to capture the a posteriori mean and covariance shown here, and then retracted back. The variables related to the state and the noise are indicated with letters D and Q respectively, and the sigma point weights are introduced here. The correction phase is accomplished by passing the state error covariance through the measurement function. Next, the Kalman gain is computed, shown here, and the state estimate and covariance matrix P of k plus 1 evaluated at k plus 1 are both updated. The control system produces a control input, as we mentioned before, indicated by U sub C, which is designed to nullify the error between the actual state and the desired state. Like the formulation itself, the controller design on TSE3 allows us to treat both translational and rotational motion simultaneously. In this work, a backstepping controller first introduced by Nazari in 2018 was used to accomplish a variety of tracking problems. The definition of all tracking states for all of the states are shown here, and the control law is defined as follows, where K is the positive definite control matrix consisting of K21 and K22, which in turn can be tuned to adjust the rotation and translational performance of the spacecraft. Phi is the configuration error function and is defined as follows, with L and L dot being functions of G and are defined here, and with S and S dot being operations taking SO3 to R3 as follows. Pan is a Saturnian moon of especially unusual shape. It was chosen because of the challenges it poses, first in its shape, but also in the environment in which it resides, where it is occluded by the precession of Saturn's rings and the various dynamic dust and radiation environments. This work considered specifically the non-spherical nature of Pan, and the other aspects are forward work. Here we see the controlled orbit around Pan and the associated parameters of Pan itself. The spacecraft is a rigid body with the following physical parameters as well. It was modeled with a mass of 60 kilograms, but other masses were tested as well, and there was no significant change to the dynamics, thus implying extensibility of this method to larger spacecraft. Future work includes optimization and guidance system implementation to minimize control effort, which you can see peaking at the initial orbital insertion, and to allow for orbit transfers or more robust applications. The filtered and ideal orbit, shown here in black and dashed red respectively, are nearly overlapped with one another, while the very noisy measured state can be seen in gray in the background. This illustrates the efficacy of the filter. Here we can see the error in each of the directions and attitudes, noting that it remains within 3 sigma deviation boundaries at all times following initial convergence. Bennu was the next object of study. Compared to Pan, it's relatively spherical, but still nowhere near as spherical as Earth or even Saturn. Bennu's properties are displayed here. In this example, the objective was to test out a hovering case, in which the goal was to center the spacecraft above a surface feature of interest. The control effort and convergence is comparable to the previous case featuring Pan, with high control effort that rapidly converges. Also similar to the Pan scenario, the filtered and ideal cases, shown here in black and dashed red respectively, remain essentially overlapped following initial convergence and demonstrating filter efficacy. Following convergence, the error remains well within the 3 sigma bounds. We have presented a novel rigid body spacecraft navigation and control scheme developed in Lie group SE3 and its tangent bundle TSE3 in the presence of stochastic processes in the system. In the mathematical framework presented here, the geometric characteristics are well preserved, and translational and attitude motions are treated simultaneously. Hence, this formalism allows for the coupling between orbital and attitude motion of a spacecraft to be accounted for. This coupling can't be neglected in the rigid body spacecraft motion around small, irregular bodies because of their highly perturbed environments. The estimated results obtained using an unscented Kalman filter used a Lyapunov-Morse-based feedback control with backstepping law to estimate the control system states with noisy measurements. The methodology used here is to prove that the augmentation of a stochastic estimation control and dynamics in TSE3 provide a reliable, functional method of guidance and navigation around small irregular bodies. The numerical results, confirming the theoretical expectations, showed that the navigation and control system presented here is capable of conducting and navigating a spacecraft towards a desired orbit and position in space. Future work will focus on testing the robustness of the stochastic estimation and control scheme presented here. Potential interesting cases include multi-body dynamics, orbit transfers, and R-pod operations. The existing results can be improved considering factors such as SRP, multi-body dynamics, maybe more spherical harmonic terms above the order of C22 and C20 as is needed. Furthermore, the results presented here only included simple logic, since logic development and design was outside of the scope of this work. Hence, another relevant improvement could be done through the implementation of a guidance system for the orbit tracking problem, far more robust than what we presented here. Special thanks to Dr. Julio Benavides, now at Odyssey Space Research, for his assistance in the coding development of this project, and to Martin Brassard of Mainz Paris Tech for his assistance with developing the UKF. Thank you for attending my talk. I have another one on Tuesday, which is the special Artemis session discussing the dangers of lunar dust and high velocity ejecta from lunar landing plumes. I hope to see you there as well. Thank you.